The Milky Way, our galactic home, is a barred spiral galaxy stretching approximately 200,000 light-years across, a cosmic city teeming with billions of stars. At its heart lies the galactic bulge, a bustling metropolis of stellar activity that captivates astronomers and dreamers alike. This region, denser than any other part of the galaxy, contains millions of stars packed into a relatively small volume, making it up to 10 million times denser than the quieter suburbs where Earth resides in the Orion Arm. Imagine a cosmic downtown where stars are so close, sometimes just 5 light days apart, that another star could sit just beyond Pluto's orbit in our solar system. This density creates a chaotic dance of gravity, with stars moving in random directions, unlike the orderly rotation of our spiral arms. The galactic bulge is not just a stellar crowd, it's a historical archive. Some of its stars are among the oldest in the Milky Way, formed billions of years ago when the galaxy was young. These ancient stars, moving in all directions and planes, give the bulge its elliptical, almost spherical shape. Yet, amidst this chaos, new stars are born. Regions of star formation produce massive youthful stars less than 100 million years old, adding vibrancy to this ancient core. The interplay of old and new stars makes the bulge a dynamic hub, a testament to the galaxy's enduring life cycle. At the center of this cosmic metropolis lies Sagittarius A, a supermassive black hole with a mass 4 million times that of our Sun. Spanning roughly 32 million miles, about the distance from Mercury to the Sun, this black hole is a gravitational titan. Despite its fearsome reputation, it's not a threat to the galaxy at large. Black holes, even supermassive ones, are small compared to the galaxy's vastness, consuming only nearby material. Stars orbit Sagittarius A safely, and its energy emissions, though immense, are invisible to the naked eye from Earth due to vast distances and intervening dust clouds. These dust clouds are the galactic bulge's veil, absorbing most visible light and obscuring our view of the center, 26,000 light-years away. To pierce this veil, astronomers use infrared, X-rays, and gamma rays, revealing a core so bright it would dominate our night sky if not for the dust. NASA's images in these wavelengths show a dazzling center, alive with energy from the black hole's accretion disk, a swirling ring of gas and dust spiraling inward, heating up and emitting intense radiation. This process explains why the galactic center outshines the rest of the Milky Way, a phenomenon once mistaken for a mega-sun. Recent observations, however, have sparked debate about Sagittarius A's activity. Some evidence suggests it may be leaking jets of gas, indicating it's more active than previously thought. Unlike the active galactic nuclei of quasars, which blaze with energy, Sagittarius A is relatively quiet, but these jets hint at occasional feasts on nearby gas clouds. This claim is controversial, as the black hole's activity level is still under study, and some astronomers argue it remains largely dormant. Clarifying this requires more data, but the possibility of an active core adds intrigue to our galaxy's heart. Beyond the bulge, the Milky Way's structure is complex. Its spiral arms, like the Orion Arm where Earth resides, are calmer, with stars spaced 4 to 5 light-years apart. This vast emptiness, most of the galaxy is dark, empty space, contrasts sharply with the bulge's density. The galaxy's shape is not a perfect disk but warped, possibly due to collisions with smaller galaxies, like the Sagittarius dwarf galaxy 6 billion years ago, or the gravitational influence of a tilted dark matter halo. Dark matter, invisible yet massive, surrounds the Milky Way, shaping its structure. This warping is common among spiral galaxies, with nearly half showing similar distortions, making our galaxy a typical yet unique member of the cosmic family. The galactic bulge and Sagittarius A are compelling because they reveal the Milky Way's dynamic nature. A blend of ancient stars, new formations, and a supermassive black hole that both anchors and energizes the core. The controversy over Sagittarius A's activity underscores the ongoing quest to understand our galaxy, a quest that continues to captivate scientists and stargazers alike. The Milky Way is a marvel, but it's just one piece of a far grander cosmic puzzle. Zooming out from our galaxy reveals structures so vast they defy comprehension, from glowing walls of galaxies to mysterious voids that challenge our understanding of the universe. These phenomena, like the South Pole Wall and the Hercules-Corona Borealis Great Wall, captivate us with their scale and beauty, while speculative ideas, such as universe collisions, spark debate among scientists. Together, they paint a picture of a universe both awe-inspiring and enigmatic. One of the most striking features of the cosmos is the South Pole Wall, a colossal structure stretching 1.37 billion light-years across, dwarfing the Milky Way's modest 200,000 light-year width. This wall is a filament of roughly 100,000 galaxies, each a glowing dot containing billions of stars. With a quadrillion stars, 10 followed by 15 zeros, it's a testament to the universe's immensity. Located 500 million light-years from Earth, the South Pole Wall is invisible to even the most powerful telescopes because our own Milky Way's brightness and dust clouds obscure it, much like city lights drown out the stars. Scientists detected it through redshift measurements, which reveal how galaxies move as the universe expands from the Big Bang. This discovery highlights the universe's web-like structure, where galaxies form chains and walls separated by vast emptiness. Even more staggering is the Hercules-Corona Borealis Great Wall, a superstructure spanning 10 billion light-years, about 10% of the observable universe. Detected via gamma-ray bursts, the brightest electromagnetic events known, this wall suggests clusters of galaxies far beyond our reach. Gamma-ray bursts are rare, occurring once every few million years in a galaxy like ours, so multiple bursts from one region signal an immense concentration of galaxies. These structures are compelling because they evoke a sense of cosmic architecture, with galaxies strung together like pearls on a string, shaping the universe's large-scale structure. They remind us that our Milky Way, vast as it seems, is a mere speck in the cosmic tapestry. Among the universe's brightest beacons are quasars, the luminous cores of active galaxies powered by supermassive black holes. These cosmic powerhouses, like those in the huge large quasar group spanning 4 billion light-years, emit radiation tens to hundreds of times stronger than all the stars in the Milky Way combined. At the heart of a quasar, a black hole, sometimes 800 million times the sun's mass, devours surrounding matter, forming an accretion disk that spins at nearly light speed. The intense gravity and friction heat this disk, producing dazzling energy. Quasars also launch jets of particles from their poles, visible in radio wavelengths, adding to their brilliance. One quasar, 13.1 billion light-years away, formed just 690 million years after the Big Bang, making it one of the oldest objects known. Its brightness, 4x 1014 times that of the Sun, allows us to study the early universe, earning quasars the title beacons of the universe. The huge large quasar group containing at least 73 quasars is a gravitational marvel, weighing 6.1 quintillion times the Sun's mass. Its scale, requiring light nearly as long as Earth's existence to cross, captivates the imagination, showing how black holes and galaxies cluster to form the universe's scaffolding. Quasars are compelling not only for their brilliance, but also for their role in revealing the universe's history and structure, offering clues to how galaxies evolve over billions of years. Yet the universe isn't just about light and matter. It's also defined by absence. The Eridanus Supervoid, or cold spot, is a vast emptiness nearly 1 billion light-years wide, formed 380,000 years after the Big Bang. Capable of holding thousands of galaxies, it contains fewer molecules than an empty room on Earth. This void is compelling for its stark contrast to the crowded galactic walls, evoking a sense of cosmic desolation. However, its origin is one of the text's most controversial points. Some scientists propose it resulted from a collision between our universe and another, a speculative idea rooted in the multiverse theory. This theory imagines our universe as a bubble among infinite others, with the supervoid formed when another universe stole material during a brief connection. While poetic, This hypothesis lacks empirical evidence, as the multiverse remains untestable with current technology. Most astronomers attribute voids to natural fluctuations in the early universe's density, making the collision idea a fascinating but contentious outlier. These cosmic phenomena, walls, quasars, and voids, reveal the universe's dual nature, vibrant and teeming in some regions, eerily empty in others. The South Pole Wall and Hercules-Corona Borealis Great Wall showcase the universe's ability to organize galaxies into massive structures, while quasars highlight the raw power of black holes. The Eridanus Supervoid, whether a relic of density fluctuations or a speculative multiverse event, challenges us to rethink the cosmos's boundaries. Together, they make the universe a place of wonder and mystery, where every discovery raises new questions. The study of these structures relies on advanced techniques, like redshift for galaxy walls and X-ray or radio observations for quasars. Future telescopes, such as the James Webb Space Telescope, may reveal more about these distant phenomena, refining our understanding of their formation. For now, they stand as monuments to the universe's complexity, inviting us to marvel at its scale while grappling with its unknowns. The controversy over the supervoid's origin underscores the limits of our knowledge, reminding us that science thrives on debate and exploration. As we gaze at the Milky Way's spiral arms or ponder the vast walls of galaxies, the question arises, what is humanity's place in this cosmic expanse? Our planet, nestled in the Orion Arm, is a tiny speck in a universe teeming with wonders and dangers. From rogue planets drifting in eternal darkness to the tantalizing possibility of warp drives, the future of human exploration is both thrilling and fraught with challenges. This final part explores the mysteries of rogue planets, the ambitious dream of interstellar travel, and the steps we must take to become an interstellar species, all while navigating the speculative ideas that spark both excitement and debate. Rogue planets, those nomads, orphans, sunless, unbound worlds, are among the universe's most haunting phenomena. These planets wander the cosmos without a parent star, cast into darkness by gravitational chaos, or born alone from collapsing gas clouds. Their existence is compelling, evoking a sense of cosmic loneliness. Imagine a world where eternal night reigns, with no sunlight to warm its surface or spark life. One rogue planet, just 20 light-years from Earth, defies this desolate image with a magnetic field 4 million times stronger than our planet's, generating auroras that dance across its atmosphere. These light shows, possibly aided by a moon, make rogue planets not just desolate but strangely beautiful, a testament to the universe's ability to surprise. Simulations suggest billions of rogue planets may drift through the Milky Way, outnumbering stars. Detecting them is a challenge as they emit no light and lack a star to betray their presence. Astronomers use gravitational lensing, where a rogue planet bends and magnifies a distant star's light, to spot them. Confirming their rogue status requires years of observation to rule out an unseen parent star. So far, at least 70 rogue planets or candidates have been identified, a small fraction compared to over 5,000 exoplanets in stellar systems. The possibility that these planets carry moons adds intrigue. Could these moons harbor life, shielded from the harsh cosmos? This question captivates scientists, as it challenges our assumptions about where life might thrive. However, the claim that a rogue planet could disrupt Earth's orbit, pushing it into a frozen wasteland, is controversial. While theoretically possible, the odds are vanishingly small. The solar system's stability, anchored by the sun's gravity, makes such an event unlikely within billions of years. Jupiter's massive presence further protects Earth by deflecting potential intruders. This scenario, while dramatic, risks exaggerating the threat without statistical context. Instead, rogue planets are more significant for what they teach us about planetary formation and the galaxy's diversity, not as imminent dangers. The dream of exploring these distant worlds or finding new homes beyond Earth hinges on overcoming the vast distances of space. Current rockets like SpaceX's Falcon Heavy travel at speeds that would take 113,000 years to reach Proxima Centauri, our closest star at 4.2 light-years away. Even the Parker Solar Probe, the fastest human-made object at nearly 500,000 mph, would need millennia to cross such distances. This limitation makes interstellar travel a daunting challenge, but the concept of warp drive offers a tantalizing solution. Proposed by physicist Miguel Alcubierre, the warp drive would compress space-time in front of a spacecraft and expand it behind, allowing travel faster than light without violating Einstein's relativity. Inside this warp bubble, the ship remains stationary while space-time itself moves. This idea is thrilling, as it promises to shrink cosmic journeys from millennia to years. NASA's 2069 interstellar mission aims to reach 10% of light speed, potentially using a modified warp drive design resembling a donut-shaped ring, rather than a perfect circle. This vision of a probe reaching Alpha Centauri in 44 years ignites hope for humanity's interstellar future. However, the concept is highly controversial. The energy required for a warp drive is staggering, equivalent to the mass energy of Jupiter. Current physics offers no practical way to harness such energy, and the technology remains theoretical. Claims of a 2069 mission may overstate progress, as no concrete plans exist, and the Alcubierre drive relies on exotic matter, which is hypothetical. Scientists are exploring alternatives, like ion propulsion, which accelerates gas particles for efficient, slow but steady travel, or laser-powered drones using nuclear or antimatter reactions. These are more feasible but still far from achieving light-speed travel. Despite these challenges, the pursuit of interstellar travel is a compelling call to action. Colonizing Mars is a critical first step, serving as a testing ground for technologies needed to settle distant worlds. Mars's thin atmosphere and cold temperatures require terraforming, warming the planet, increasing atmospheric pressure, and creating an ozone layer to shield against solar radiation. These efforts will teach us how to make alien worlds habitable, preparing us for exoplanets in systems like Proxima Centauri, where planets in the habitable zone might support liquid water. The vision of humanity fleeing a dying Earth as the sun expands in 7.5 billion years is dramatic but grounded in science. Long before then, the Milky Way's collision with Andromeda in 4.5 billion years could disrupt stellar systems, though life on Earth would likely end due to the sun's evolution, not the collision itself. The idea of contacting extraterrestrial life via warp drive is another compelling prospect. If life exists, it's likely in the middle regions of galaxies, where radiation and star density balance to support complex chemistry. The Milky Way's vastness, with billions of stars and potential planets, makes this a thrilling possibility. However, the optimism about warp drive enabling such contact must be tempered. The technology's theoretical nature and immense energy requirements mean it's not a near-term solution. Instead, missions like NASA's Nancy Grace Roman Space Telescope, set to survey rogue planets, and the proposed Cleopatra mission, using parallax to measure distances, will expand our understanding of the galaxy, paving the way for future exploration. The universe's mysteries, from rogue planets to galactic collisions, remind us of our dual role as observers and explorers. Rogue planets challenge our notions of where life might exist, while the dream of warp drive pushes the boundaries of physics. Controversies, like the exaggerated threat of rogue planets or the feasibility of faster-than-light travel, highlight the need for rigorous science to ground our ambitions. As we develop technologies to colonize Mars and beyond, we're not just chasing stars, but ensuring humanity's survival. The Milky Way, with its warped disk and hidden core, is a microcosm of the universe's complexity, urging us to look up, dream big, and take the first steps toward the stars. The universe is not just vast and structured, it's also delightfully strange, filled with phenomena that stretch our imagination. From pulsars that devour their companions, to the strongest material known, dubbed nuclear pasta, and planets where glass rains from the sky, these cosmic oddities captivate us with their sheer weirdness. They remind us that the Milky Way and beyond are not only places of grandeur, but also of quirks that challenge our understanding of physics and inspire awe. Consider the Black Widow pulsar, a neutron star spinning at breakneck speeds, emitting beams of radiation like a cosmic lighthouse. Located in our Milky Way, this pulsar earns its sinister name by consuming its companion star, stripping away its material in a deadly dance. The pulsar's intense gravity and magnetic field pull gas from its partner, creating a glowing trail that emits X-rays. This phenomenon is compelling because it showcases the universe's brutal beauty. Stars not just shining but actively reshaping their surroundings. Unlike typical stars, pulsars are the remnants of massive stars that exploded as supernovae, leaving behind dense cores. The Black Widow's behavior, while extreme, is well documented, making it a fascinating example of stellar evolution. Even stranger is nuclear pasta, a material theorized to exist inside neutron stars, including pulsars. Formed under crushing pressures, this substance consists of atomic nuclei arranged in shapes like lasagna, spaghetti, or gnocchi, hence the name. It's considered the strongest material in the universe, far tougher than steel or diamond, due to the immense gravitational forces compressing it. Nuclear pasta is compelling for its blend of the familiar, pasta shapes, and the alien, extreme physics. While its existence is supported by simulations, direct observation is impossible with current technology, making it a slightly controversial topic. Scientists rely on indirect evidence, like the behavior of neutron star collisions, to infer its presence, but the idea captivates for its ability to make the unimaginable tangible. Then there are exoplanets with conditions so alien they sound like science fiction. Take HD 189733b, a gas giant 64 light-years away, where silicate particles in the atmosphere form glass that rains sideways due to 5,400 Mach winds. This vivid image of a glass-raining world, glowing blue in visible light, captures the universe's diversity. Such planets, while extreme, are grounded in observations from telescopes like Hubble, which detect atmospheric compositions. The idea of glass rain is less controversial than poetic, illustrating how exoplanets expand our view of what planets can be. These oddities, pulsars, nuclear pasta, and glass-raining worlds, highlight the universe's creativity. They also fuel our drive to explore, as missions like the James Webb Space Telescope seek to uncover more about these phenomena. The Black Widow pulsar shows stars can be predators. Nuclear pasta reveals the strength hidden in stellar remnants, and alien worlds challenge our notions of habitability. Together, they urge us to keep probing the cosmos, embracing its strangeness as a call to curiosity and discovery.